Okay, so which one of these, why would A and C be ridiculous answers? Because they have a negative in front of, and that would cause the graph to be, something like this. And we don't have those. So we really only have two choices. We can see from the graph that it's what kind of graph? Growth or decay? Good. Got to see if that kid pays attention. It is decay, so which is my only choice? B. Okay? Is this growth or decay? Growth. And it's been moved which direction? Left, right, up, or down? That's up. So, why is this one wrong? I mean, it's growth, right? Didn't get shifted up, but you're right. I think, Mr. Singh, you said A. You are correct, right? It's been shifted up one unit. The others were upside down, so they didn't even meet the criteria of what we needed. What about this? Growth or decay? Growth, good. Right, because the growth factor is larger than 1. Which way is it moving? Left, right, up, or down? Left. Did you say B? D. Oh, I agree with you there. Yeah, this one's been shifted up, and these two are completely upside down. So, yeah, you're right. Okay, and I think that is the last example for this set of notes. Make sure you're drawing did I go too fast through any one of those for those of you who are not doing it on digital and need to draw a quick sketch of the graph? Yes, 17 or 18? 18, sure. So even if we did do, start our quiz on Monday, then you would have time to study the Monday night and look things over in case there was something that didn't make sense. Then you could fix it on Tuesday. But I'm sure there'd be problems like this that you'd be able to knock out and, not have to do.
Can you go back up to 17?
Yes. There's 17. It just all depends on how far we get in the notes for section 3. So did you get that? Kind of just everything shifted up one? Okay. Okay, so this is a story problem situation. I'm going to try to limit the types of story problem situations. But here's a population that starts out at 110,000, grows 5% each year for 14 straight years. So tell me what I would need to put in here for this equation. We've kind of done these already. We should know what goes in the first blank, and we should be able to figure out what goes in the second blank because we know every percentage starts out at 100%. This one just happens to be going up 5%. So it does go up to 105%. You're right. And that is good information for writing your equation. All right. So what should we put in our equation? What? 1.05. Okay. Yep. Because we talked about how you would move that over 2 places. Where does that go? In the first blank or the second one? Second. That's your growth factor. I should definitely get rid of those lines under there. And what about the this first value? It's 110,000, right? It's your starting amount. Man, my hundreds place looks sick. Let's get a better look at 0 in there. So that's not too bad. And how are you going to figure out the population after 14 years? Put it in your calculator. You're going to reach down, grab that calculator, which you should be doing right now. If you don't have your calculator with you, I suggest you use your computer or other electronic device. Okay? Sorry, was there a question from somebody? If you go to pages or modules, you can go to modules. That would be where you can find Chapter 8 or Unit 8 or... it'd be 8.3. 8.3 story problems. Be able to find this. I got 217,000. What'd you get? 792. We'll round to the whole nearest whole number, folks. No fractional people. We are not that kind of people, right? Yeah. Cutting people up. You know, that's disgusting. Okay. No fractional people. Yeah, and it's not the one you want. It's in a classroom. That's why I put in giant letters, printer 513, 515 right there. Save. When you print inside of somebody's classroom, you're wasting paper and you're not going to be getting what you want. You didn't print to the wrong place, did you?
No, I did.
Okay. Yes. Literally, you are correct. Question 2. One type of uranium has a daily radioactive decay of 0.6%. If 20 pounds of this uranium is available today, find how much will remain after 50 days. Now, radioactive substances have what's called a half-life. They are in the process of decaying all the time. Not just once a day, not just once an hour, constantly. So many times are they're being cut in half so much. It's a continuous process. Now, the interesting thing is, for this question, you don't even have to come up with the equation. They gave it to you. So, if you're thinking, oh my goodness, this is a story problem. This particular one, because it's a little bit more complicated, it actually is of a different form, a slightly different form. So instead of making you figure it out, I figured I would give it to you. So where are you going to put the 50? Where the T is, right? So now if you're typing this on a calculator, you would have 22.7 in parentheses. You'd use the caret, but look at what I'm going to do next. I'm going to use parentheses around the other part. So please make sure you can use your calculator right now. Okay, so we should have had 14.8. Did anybody not get 14.8? And I need to come check what they typed on their machine. Okay, let me look. Ah, you forgot the times sign. See how I put it? Well, yeah, I could. So you get the times sign, so it knows to multiply those two numbers together. Not at the moment. Okay. Okay. Thank you. How many total? Yeah, I will, but he wanted it. There are 12 questions. All right. Did you need me to go to question 2? Okay. Question 3. This particular equation you've been given models the number of college students who study overseas each year from 1995 through the year 2006. In the equation, y is the number of American students studying overseas or abroad, and x represents, it's interesting they use that word, abroad. And X represents the number of years after 1995. That's a critical and piece of information. X is the number of years after 1995. So what would you plug in for 1999? You'd plug in an X value of 4. Thank you very much. Do not plug in 1,999 or you are going to get the wrong answer in a hurry. Okay, it's really important. That little piece of information is extremely important. So take your machine, find your value for 4 years. For those of you who don't know, you can come down here to the search bar at the bottom of the screen and use your calculator, 84,921 times, and you didn't use I think you just used a parenthesis, you didn't have to, 1.093. Now, by the way, folks, what growth rate are we talking about here? What is this growth rate? 1.093. Can you tell me what rate we're growing at? You better be able to look at that and say, it is not 0.93%. It is 9.3%. Exactly. Right? If you move that over, we had 109.3%. So that is a 9.3% growth. That's a decent growth, which is why, oh, daggone it, I lost it. Oops. Oh, there it was, the 121,000. Oh, yeah, there is a calculator. Okay, 121,198. 121,198. Assuming this equation continues to be valid in the future, use this equation to predict the number of American students studying abroad in 2019. That is, what are we plugging in for X? 24. Which makes sense because that's 20 years difference from 99 to 2019. So, figure it out. I got over 700,000, so if you get over 700,000, you're in good shape. Well, to have this kind of growth rate for 24 straight years, you would be growing rather quickly. You would have a lot of, if this were a city, you know, that you would be expanding and adding new roads and hospitals and power lines and sewage and everything would be growing quickly. Be a lot of turmoil. You'd be mad because your roads were torn up all the time. So 717,627 when you plug in that. You need to be able to do that. What's the growth rate on question 4? This formula gives the number of cellular phone users in some country for the years from 94 to 2006. What's the growth rate? I got to vote for 22%. You agree?
Yeah.
That is true. 22%. That's a good clip. Sounds like being a cell phone salesman would be a good job in this particular area if it's going up by 22% each year. Use this model to predict the number of cell phone users in the year 2008. What are we going to use for X? Are we going to use 2008? Years above 1995. Okay, so how many years are there from 95 to 2008? 94 years?
No, 1994 to 2008.
Oh, okay. Yeah, okay. I gotcha. All right, thank you for correcting me. I appreciate that. I was like, what? I was like, I'm pretty sure they're better than that. Okay. So we're starting at 94 to 2008. So, how many years are we talking about? 14 years, thank you very much. Let me come around and see what you get for that kind of work. Yes, we used y in the equation. You're right. 275.
Excuse me.
Okay.
Okay, let's see.
4 bacteria are placed in a petri dish. How'd you count those out? You know what I'm saying? Ah, just want 4. Okay, that's it. Yeah. Okay. So some of these problems seem a little bit ridiculous. Okay, how did you count them out? I mean, the population will double every day. The formula for the number of bacteria in the dish on day T is given to you. Right there it is. T is the number of days after the 4 bacteria are placed in the dish. Before that they were at a party, but now they're in the dish. How many bacteria are in the dish 6 days after the 4 bacteria are placed in the dish? What are we plugging in for T? 6. Yep. Folks, it's not, we haven't even gotten to the difficult stuff, right? Or the more difficult stuff. This stuff is pretty easy. That's why I wanted to start with these 5 examples. Okay? So what are we getting?
256.
256. How long are, how about 30 days? How about 1 month? 1 month. That's why you use a calculator.
Oh, that's not right.
429496726.
What was it? 429.
496.
496.
7296.
7296. I always like to write them out and put my commas in because I won't know.
4 billion.
You're right. Takes 30 days to reach 4 billion. Doesn't take that long. Exponential growth starts out slow and then grows quickly. Time is, in this case, bacteria wouldn't be your favorite thing, but,
Oh, you just got that. You're stupid.
Now, the compound interest formula. Obviously, we're going to focus more of our attention on this on Monday. Okay, but ignore the second equation for now. I just want to focus on this equation. Now, believe it or not, this equation is the same as this equation. They're identical. One of them looks more complicated, obviously, but this is how your money grows, and it also is how credit card companies end up charging you a lot of money too. So it works for and against you, depending on if you're good with credit cards or not. So how do these two equations relate to each other? That's the question I want to discuss. The A value is like the Y. It's the amount of money you're going to have at the end. The principal is like your starting amount. That's the amount of money you start with. Okay, in our equation, what are we starting with? $16,000. This is the part that people struggle with. So I'm going to try to be very careful as I draw this. That right there is the growth factor, which leaves one thing for X, which is the time, T. It is, but it won't be. Okay? Now, how many years are we leaving the money in the account? 7 years, right? So that's going to go out here. Now the part inside the parentheses that we need to worry about, and maybe I should move that 7 over a touch. Because we're also going to have the value of n. Now, the part that we need to discuss more, which we'll get into a lot on Monday, is what does it mean by compounding? Okay. Okay. Now the compounding factor, in this particular problem, it says that the compounding factor is annually. That means that the n value is equal to 1. That means they're going to give you interest one time in a year. How much are they going to give you? Looks like they're going to give us 12%. That's big. That's nice. Now, we could change that compounding factor. We could say compounded quarterly. How many quarters are there in a dollar?
4.
4. So that would be 4 times a year. In other words, I would take the 12% and split it into 4 pieces. Every quarter, I would give you one of those pieces. Now, the nice thing is, so that would be 3%. I would give you 3% every quarter of a year. But guess what? If I'm dishing out 3% in the first quarter, and then I go to the second quarter, I'm giving you money based upon what you already have. What that means is you're getting more money because you're getting interest upon the interest. See, I'm paying you not only for the original amount, but I'm paying you for the amount that I gave you the first time. That's why this thing grows so nicely. What if I compounded monthly? How many times a year would monthly be? 12 times a year. So I would take the 12% interest, split it into 12 pieces. Each one of those would be 1%. Every month I would give you 1%. You would make even more money. What if I compounded daily? That'd be 365, right? So I would take 12% divided into 365 little tiny pieces, and every day give you one of those pieces. You would get even more money. So, what do credit card companies compound? What compounding factor do credit card companies use? How often do you have to pay the bill? Monthly. They compound monthly. So they have a ridiculous rate, and they compound monthly. So if you get behind on your payments with a credit card, it adds up in a hurry. So let's finish this one problem and be done today. So 1 plus. Now, the interest rate is 12%. What is that as a decimal? 0.12. And the compounding factor here is a 1. You notice in the formula, n shows up twice in 2 places. Okay? What's the part inside the parentheses there that I highlighted with the blue? What is that number? Well, tell me what that number is. 1.12, right? That's not that so this problem really wasn't that difficult because I didn't even change the compounding factor to something more interesting. You work this out while I come check your notes. You work this one out. Give me an answer by the time we walk out the door. Need more than that. You need more than that, man. You can test time too. Quiz. Thank you. Okay. All right, so actually, Okay, what do we get as a number here? 16,000. 1.12 to the 7th power. 35,370. Oh, 371. Yep, you're right. Rounds to the nearest dollar. You are correct.